Yeah, so traditionally there's been two extremes in machine learning and artificial intelligence. Machine learning has tended to not have any stories or prior knowledge baked into it. It just learns from data, and it almost knows almost nothing when it gets started. On the other end of the spectrum, a lot of the work that was done, for example, at MIT in for a long period of time, the 80s, 90s, early 2000s, were around artificial intelligence, expert systems, Bayes nets, systems where humans could program in expertise into the computer. And so those were kind of extremes. In one extreme, the first extreme, it takes a lot of training examples. If you want to teach a computer what a kitten looks like, then you get a picture of a kitten, you say that's a kitten. You get another picture, and you say that's a kitten. You do that about 10,000 times. Now it knows what a kitten is. If you want to teach it a kazoo, you get 10,000 pictures of a kazoo, and you say kazoo, kazoo, kazoo. So it's a lot of human time to train it. On the expert system side, it's also a lot of human time because people were typing in rules. What is the difference between a kitten and a puppy? I don't know, the kitten has whiskers, the kitten has triangular ears. So you have to type in all of these details. It tends to be very brittle because if something a little bit changes, there's a different kind of puppy that doesn't look like, the average puppy or something like that, then, maybe the rules don't apply. So the rules, you type them in, takes a lot of time, it's brittle. The training takes a lot of time, and it learns from data, which is great, but you sort of can't tell it anything and you don't know what it's thinking. So what we've done is sort of find a best of both worlds. And they're sort of soft rules, if you will. The system is learning essentially a story about how the data came to be. So, in the case of looking at an image, the data on the image came to be because light reflected off of a kitten and hit the aperture of your camera, and the kitten had, legs and a face and eyes and so forth. So, but they're very general, like typically 50 lines of code. So it's a very simple set of rules. And we find that with just a few rules and say 3 or 4 training examples, that's a kitten, that's a kitten, that's a kitten. Generally kittens have whiskers and they probably have triangular ears. That amount of, that kind of sweet spot does better than programming 100,000 rules or pointing at 10,000 or 100,000 kitten pictures. It does better than either of those extremes. Within our system, so how does this relate to deep learning, existing deep learning or rules-based systems? Essentially, any deep learning system today or any rules-based system could be rewritten in our system, could be expressed as a special case. So the way to think about it is if Python's a programming language or C is a programming language, in a programming language you could write a program. So you might write a program to, I don't know, spit out the alphabet or something like that. In Bayesian program learning, in Bayesian programming, a deep learning system would be one program, and an expert system would be another program you could write. So what we've really done is come up with a unifying fabric that allows you to express essentially any machine learning probability distribution, any statistical machine learning system, and then sort of combine them in a completely rigorous and unified way with one another and in gradation. So it's a different way of thinking. Instead of going and grabbing modules, machine learning modules, you just write down a initial story for how your data came to be, and then you push compile, inference compile. And what happens is under the hood, our cloud examines the story you wrote and figures out how to fit it to the data and whether the story needs to be modified to fit the data, and then tries modifications to fit the story to the data, and also tells you which data doesn't fit the story. So one of the things that's most important about our approach is that it is modular and composable and has abstraction boundaries the same way regular programming does today. So today, because we've built debuggers and profilers and compilers and regression testers and all this great machinery that helps programmers program, with regular conventional programming today, you can have a team of 250 programmers, and they can build something like Google Maps. They can each take on, they can also, I can say I'm going to work on the UI, and somebody else can say I'm going to work on the database backend, and we don't need to look at every line of code that each other write. We can stick them together because we have APIs. We have ways of abstractions for sticking together software. That has not existed in machine learning until today. So basically the limit for machine learning has been essentially 1 or 2 people working on a system, on an algorithm. They have to keep all of the code in their head. If you bring, when I put a third person traditionally on a machine learning project, it would just slow it down and make the outcome riskier and less likely to succeed. So there's really a modularity and a scalability limit before. One of the things that Bayesian programming does is it makes machine learning like regular programming, so that different individuals and different teams can work on different parts, and they can be put together. And that's what leads to open source. That's what leads to the sort of software eating the world, is this ability to continually reuse other people's software and incorporate it into new and better systems. And now we're going to be able to do that in machine learning, which I think is one of the most exciting things about Bayesian programming.